Across billions of light years, galaxies sit with the same spacing. Why? Because a frozen sound wave from the early universe set a ruler. You can feel that ruler in galaxy maps and microwave light. Immediate takeaway: patterns repeat because physics repeats under the same rules. Waves, gravity, and statistics stamp familiar shapes across huge distances. Some shapes are literal duplicates, created by space-bending light around mass. Others are harmonies preserved since the first few 100,000 years. We will unpack those echoes fast, with clear examples and numbers. By the end, repeated shapes will feel expected, not spooky. Picture a faint ripple racing through a glowing, early universe plasma. Baryon acoustic oscillations are fossil sound waves in matter. They give us a cosmic ruler to track expansion precisely. Hot photons pushed on protons and electrons, while gravity pulled everything inward. That tug and push launched pressure waves across the young universe. When atoms formed, the waves froze, leaving a preferred separation scale. That comoving shell is around 150 megaparsecs, about 490 million light years. Galaxies formed slightly more often near that radius from each seed. Example: in real terms, we measure a bump in pair separations. The Sloan surveys saw it crisply across millions of galaxy pairs. eBOSS and DESI refined it further, mapping the ruler over time. With that fixed scale, we read the universe's expansion history. Net result: repeated spacing is a sound wave fossil, not magic. Now zoom close to a massive galaxy cluster, warping the background. Gravitational lensing bends light, making one object appear multiple times. That matters because duplicates can look like cosmic copying at first. Mass curves spacetime, so photons take several paths to your telescope. Those paths arrive with delays and different stretch and orientation. If alignment is perfect, you see a bright Einstein ring. If slightly off, you get arcs, crosses, and mirrored pairs. The Einstein Cross shows 4 quasar images within a few arcseconds. Hubble and JWST have caught repeating supernova images with year delays. Tiny tests ask if spectra match exactly across the bright knots. If they do, you are seeing one thing viewed many times. Bottom line, literal duplicates come from curved space, not cloned galaxies. Shift the scale to swirling gas, stars, and dark matter. Self-similarity means patterns look alike across different sizes. It matters because our brains can overread lookalikes as special. Gravity pulls material together, while turbulence shreds and stirs structures. Feedback from stars and black holes punches holes and drives flows. These processes often yield power laws which lack a preferred size. So you see filaments, knots, and sheets across huge scale ranges. Molecular clouds show fractal dimensions near 2.3 repeatedly. Cosmological simulations produce matching filaments from kiloparsecs to hundreds of megaparsecs. Example: in real terms, zooming 10 times still shows similar clumps. Rule of thumb: power law physics breeds familiar shapes at many scales. So the picture is, self-similarity explains many repeated-looking forms. There is a clean spiral stamped across thousands of galaxies. Spiral arms are not lines of stars, but moving density waves. That matters because different galaxies can share the same geometry. Orbits pile up where the wave is, boosting star formation locally. The pattern rotates slowly, while stars pass through, lighting the lanes. Shear from rotation and gas sound speed set the arm pitch. More shear means tighter arms, fewer means looser, graceful swirls. The Milky Way's pitch is near 12 degrees by most fits. The Whirlpool galaxy holds near 20 degrees, a more open sweep. Across grand designs, those numbers cluster into familiar families. Example: in real terms, twin-arm spirals reappear despite different star ages. What to remember: density waves copy geometry under shared disk physics. Fade to a modeled, baby blue map of the microwave sky. A power spectrum is a chart of pattern strength by scale. It matters because that chart reveals the universe's ingredients. We decompose the sky into harmonics, like notes on a drum. Peaks mark scales where early sound waves rang the loudest. Alternating heights show how baryons weighed down those oscillations. At small scales, diffusion blurs patterns, making a soft, damping tail. Planck measured crisp peaks near multipoles 200, 540, and 800. WMAP saw them earlier, but with thicker error bars. From those peaks, we infer dark matter and dark energy fractions. Example: in real terms, matching the first 3 peaks nails densities. Net result: repeating peaks are harmonics of the primordial sound. Cut to a starfield that looks like familiar animals or faces. Pareidolia is our tendency to see meaningful shapes in randomness. It matters because the sky offers boundless chances for coincidence. Billions of stars and clouds guarantee frequent, convincing lookalikes. Big surveys also pick targets that already look unusual. Algorithms reject boring smudges, while observers chase striking features. That pipeline amplifies repetitions that feel designed but are not. Common mistake is thinking similar outlines need a shared origin. Example, in real terms, nebulae nicknamed for animals are unrelated clouds. Another case, random galaxy pairs can mimic lensing arcs by chance. With millions of tries, rare matches stop being rare at all. Bottom line, selection in psychology can mass-produce cosmic déjà vu. Now center a barred spiral with two glowing rings in view. Resonances in rotating galaxies set up repeating rings and bars. That matters because shared dynamics make similar blueprints across disks. Orbits respond strongly where frequencies meet simple ratios. A bar can drive gas inward to inner Lindblad resonances. Gas piles up there, igniting star formation in bright nuclear rings. Farther out, another resonance can sculpt a second, broader ring. NGC 1097 hosts a starburst ring near 1 kiloparsec from center. It also shows a larger outer ring, shaped by its bar. Many galaxies repeat this Turing pattern within similar size ratios. Example, in real terms, the ratio often sits near 3:1. Bottom line, resonances imprint repeating rings wherever conditions align. Pan wide across a honeycomb of galaxy clusters and long walls. Cosmic variance is the randomness left after measuring everything right. It matters because bold claims can sprout from flukes in small volumes. Limited sky patches and noisy distances make patterns seem persuasive. Statistical tests also drift when tuned after seeing the data. That a posteriori tuning inflates apparent significance, then fails on new maps. Claims of periodic galaxy spacings near 128 megaparsecs appeared. Later surveys with larger samples did not confirm a strict rhythm. The giant arc spans billions of light years, but might be rare. We need replications across sky regions and with independent methods. Example, in real terms, DESI's uniform pipeline helps prevent bias detections. Net result, some grand repetitions fade under bigger, cleaner surveys. So that curious galaxy spacing from the opening is a sound fossil. The deeper rhyme is simple, shared physics repeats across time and size. Gravity, waves, and statistics set the stencils we keep rediscovering. When you spot a duplicate, ask which of those three fits. If this clicked, consider subscribing for more clear space explainers. I will keep bringing numbers, visuals, and calm takes, no hype. Thanks for flying through the cosmic patterns with me today.